All right, good morning, everyone. So just a reminder where we finished off last time. So last time we were talking about what happens when light, which again is a wave, and again, these are our ray diagrams of our light, is going from medium number 1 into medium number 2, meaning it's going to hit a boundary between these two mediums. And again, part of that is going to be reflected back into medium number 1, and then part of it's going to be refracted, or what's called transmitted, into then medium number 2. So last time we only looked at the reflected part, and what we said was that for the reflected part, we have our incidence angle, which is the angle relative to the normal line here, and the reflected angle, also relative to the normal line, is then simply equal to the same thing. So the angle of incidence is equal to the angle of reflection, always. That's about as far as we got in that case. So next thing we want to look at then is, well, what happens then with the transmitted or refracted wave? So how is that angle, theta 2, then related to the incidence angle, which is what we call angle theta 1? So to answer this, we first have to talk about something else, or that something else is what's known as the index of refraction. So it turns out that when light travels inside of some sort of medium, it travels at a rate which is less than the speed of light. So typically what happens is it's going to move in sort of some medium. So it's going to be my medium here. What happens then is when light goes from, say, air, which is out here, we know that the speed at which air is moving here is about 3 × 10⁸ meters per second. But then by the time it gets inside of the new medium, it's going to travel at a rate v, which is then less than c. Okay? So the speed at which light is traveling less than the speed of light. Now, reason for this is multiple different ways we can think about this, but one way we can think about it is that light is a particle, which is what we call a photon. Now, what we know is that we talked about last semester when we talked about early universe, when the universe being opaque. I think we talked about this maybe this semester too. But anyways, photons coupled to charge, which basically means that as a photon is trying to move, it feels the charges that are around it, and these charges basically suck up the photon. So this medium here is typically going to be some sort of dielectric, which means that it's going to be a system or some sort of polarizable system, which means I'm going to have positive charges on one side, negative charges on the other side. So if I had, for example, a photon, so here's my photon, traveling with my speed, let's call that guy gamma because that's my photon. What basically happens then is that the photon is going to be sucked up by the positive charge. So this thing's going to be sucked up by this positive charge, be re-emitted, and then go to another dipole over here, be sucked up by the negative charge, be re-emitted, sucked up by another negative charge, re-emitted, sucked up by another positive charge, etc. Which basically means that the mean free path at which this thing is going to travel becomes much shorter than what it was traveling inside of air, because in air it's almost infinite. Which means in this case, the speed at which it is traveling through gets a lot slower because it's constantly being absorbed and re-emitted and absorbed and re-emitted by all these charges which are inside of my medium. Another way you can think about it is that the photon, again, is coupling to positive and negative charges, which means as it's trying to move through the medium itself, it's going to be constantly pulling back from all of these positive and negative charges, meaning it's going to feel like it acquires a mass. So my photon, while it's inside of this medium, becomes effectively massive, and anything which has mass has to travel at a speed less than the speed of light, because the only thing that can actually travel at the speed of light are massless quantities. But the point is, however it is you want to think about it, either the photon is constantly moving in different directions as it's being reabsorbed and re-emitted by all of these different charges, or it's moving as it has effective mass. Whichever way you want to think about it, doesn't change the point that it moves with a rate which is slower than the speed of light. So whenever my photon or light enters into some sort of medium, it's always traveling at a rate which is less than the speed of light. Now, the rate at which it is moving turns out to then be equal to c divided by n, where n is what's known as the index of refraction. Which means my index of refraction then is defined as the speed of light divided by the speed at which it travels with inside of the medium. This is what we call the index of refraction. So from here, we can see index of refraction has no units to it, because this is velocity divided by velocity, which is then a unitless quantity. Now, for the most part, the index of refraction is a constant, but it's a weird constant in the fact that it's a constant, but it's not a constant. meaning that it's a constant, but it depends on frequency. So what that ultimately means is that it's a constant for different frequencies of light. Every different frequency of light moving inside of this medium will have a different index of refraction. So in general, this quantity here will actually be frequency dependent, which means that it's actually wavelength dependent as well. So what we see for light, so for example, when I see Dalton's fantastic red shirt, what I am seeing is he's giving off a particular frequency of light, and I'm seeing that frequency of light, which which my brain interprets to be red, just like now, everybody in here, I see a particular different color. That particular color corresponds to a different frequency of light, which basically means that as different frequencies of light, i.e. different colors, move inside of this different dielectric, each one of these experiences its own different index of refraction. This thing is actually frequency dependent. Now, for our cases, most of the time we're going to be playing then with only monochromatic light, meaning we only have one frequency, so we don't have to worry about it. So we just have then this thing being a constant. But the fact that this has different index refractions for different frequencies actually gives us things like rainbows. This is actually where rainbows come from. So a rainbow is, a rainbow is actually the fact that light, in this case white light coming from the sun, where white light is actually a superposition of all possible different frequencies, is going to come through and it's going to enter into a water droplet in the air. Once it enters into the air, what happens in this case is each one of these different colors has its own different index of refraction, which means they all travel at different speeds within inside of the water droplet itself. Now, what happens is, since they all have different speeds, they want to spend the least amount of time inside of the dielectric, which in this case is the water droplet. They want to spend the least amount of time as possible. So they're all going to travel different path lengths depending on the speed at which it is that they're traveling. This is what's known as Fermat's principle. So Fermat's principle says that they all travel at different distances to try to minimize the amount of time that they spend within inside of the dielectric. So what that does is it causes what's known as dispersion. So when the white light comes in, the white light then separates into all different colors, which is what causes us to see the rainbow being all different colors. So what happens in this case then is what? I get this dispersion, the separation of light. These hit the backside of the water droplet, get reflected then to the front side, which then causes refraction. They then move outside where they're now dispersed. So they're all completely separated from each other, which allows me then to see the beautiful color of the rainbow. Now, it turns out that red is the greatest amount of deflection, where blue is the least amount of deflection. So red is bent the most, where blue is bent the least. So in this case, this is why I see where these guys are. So the red is on top because it's being bent the most, blue is on the bottom because it's bent the least. That's why I see the actual rainbow. Well, this is where rainbows come from. Simply has to do with the fact that each one of these colors has their own different index of refraction inside of a different medium, which allows me then to see the actual rainbow itself. Now, one important thing is to make sure that the sun is behind you when this happens. So if you want to actually see a rainbow, make sure the sun is behind you, because what's happening is it's reflecting off the water droplets in front of you and then reflecting back down into you. So you can't look at the sun and see a rainbow. That has to be to the rainbow to actually, or to the sun to actually be able to see it. But anyways, this is index of refraction. So the point is, light travels in at different speeds whenever it goes inside of different mediums, where that speed at which it is then going at is determined by the index of refraction of the medium itself. So that means that if I want to know how it's going to bend inside of a different medium, I need to know then what is the index of refraction of that medium. Now, what this will allow me to do, or ends up doing, is allowing me to see all kinds of interesting different things. So this fact that I have different index of refractions going from one medium to another medium allows the light to bend, which allows me to see all kinds of different optical effects. So here what you're seeing is that what the straw looks like it's here, but then it moves over here. In this case, it looks like it's bent in the opposite direction. Here there's a laser showing in, which actually shows how the light is being bent inside of this material. It's sliding out in this direction. Or showing you some more. Here's another one. So same thing here, looks like the straw is bent. Same over here, looks like the spoon is bent, all because of the index of refraction, the fact that the light is moving at different rates inside of different materials. Now, one important thing to note about your eye is pretty stupid. What do I mean by that? Your eye always follows a path of a straight line when it comes to light, which means that if light originated inside of some sort of medium, it's going to travel at a different angle. By the time it comes outside of that medium into another medium, it then changes the angle, and then our eye sees it coming to us at a different angle than what it originated at. But our eye does what's called ray tracing and wants to trace that line back to the origin, always in a straight line. It doesn't understand that light bends. Which means that when you're looking at this, the reason that this thing looks bent is because your eye is trying to interpret where that light actually came from, moving in a straight line, but it didn't come from that point. It actually came from a different point because light bent. Does that make sense? So this is what's called ray tracing. So our eye always thinks things move in straight lines. They don't move in straight lines, which causes these interesting optical effects. But again, all that's happening here is the light is moving different directions when it's in one medium as opposed to when it's going to the other. Okay with this? Sorry. So let's go back to our picture. So here, what this means then is this medium is going to have its own index refraction called N1. And then this medium here is going to have its own index refraction. Let's call that guy N2. So the angle at which it is depends then on N1 and N2. And the way that this depends on N1 and N2 is by what's called Snell's Law. So we already saw this in lab, but let's talk a little bit more. So Snell's Law. So what Snell's Law says then is, here's my boundary. So this is N1, this is N2. Here's my incident ray. Here is my refracted ray. These are my normal lines. So this is theta 1, this is theta 2. So what Snell's law says is that the index refraction N1 times sine of theta 1 must then be equal to N2 times sine of theta 2. So this is what's called Snell's law. Now, what does all of this mean? So what this basically means is what? We can determine the size of theta 1 versus the size of theta 2, depending on the size of N1 versus the size of N2. So let's look at some cases of this. And we talked about these cases in the lab, and I'm going to do it again. So case number 1 is that N1 is greater than N2. Meaning that here, I'm going to go from a high index of refraction to a low index of refraction. So what happens in this case? Well, again, from Snell's law, we know that N1 divided by N2 then is going to be equal to sine of theta 2 divided by sine of theta 1. I'm just rearranging Snell's law. So I'm just dividing both sides by N2, dividing both sides by sine of theta 1, which gives me this expression. Now, if N1 is greater than N2, that means I have a large number divided by a small number, but if I have a large number divided by a small number, what does that do to the overall number? Makes it bigger, which means that this thing then has to be greater than 1. What has to be true then is that 1 must then be greater than N1 divided by N2, which means that's equal then to sine of theta 2 divided by sine of theta 1. So what this means then is that the ratio of sine of theta 2 divided by sine of theta 1 must be greater than 1. So what does that mean? Well, remember that sine gets bigger the closer I get to 90 degrees, and then smaller the closer I get to 0. Okay? So now if I take an inverse ratio of this, what this tells me then is that what theta 1 then must then be less than theta 2. So why is that? Again, to make this bigger than 1, I need this thing close to 0 as possible, and I need this thing to be a larger number. So I want this thing to be as big as possible. So in this case, what I want is that theta 1 must be then less than theta 2. So what does this mean? So what this means then is that what? If I go from a high index refraction to a low index refraction, my light then bends away from the normal. So this is the outcome of this. So ultimately what this means is what? If here's my boundary, here again is my normal line. This is my incoming ray at theta 1, then my outgoing ray must be bent away from the normal, so that theta 2 must be greater than theta 1. So this is the outcome of this. So if I go from a high index refraction to a low index refraction, my light needs to be bent away from the normal. Case number 2. Case number 2, if N2 is greater than N1, which means I'm going to go from a low index refraction to a high index refraction. So in this case, I'm going to get N1 over N2 again must be equal to sine of theta 2 divided by sine of theta 1. In this case, this must be less than 1, because now in this case, I get a small number divided by a big number, which means that's going to be an even smaller number. So in this case, I need 1 is then less than N1 over N2, which is then equals sine of theta 2 divided by sine of theta 1. In this case, what must be true then is that theta 1 must be greater than theta 2. So if I want this thing less than 1, I need this term here to be bigger than this term. The only thing that's going to happen is if theta 1 is bigger than theta 2. Again, theta 1 is getting closer to 90 degrees. Okay with this? So in this case, what happens then is that this is bent toward the normal. So this is my boundary, and this is my normal line. This is my incoming ray, theta 1. And my refracted ray is going to be something more like this, which is going to be theta 2. Okay? So in this case, it's going to get bent toward the normal. Okay. Now, one interesting thing about this, though, is it turns out that there actually exists a particular angle that if I had it going from the one into the other one, let's say in the first scenario, where I'm going from a high index refraction to a low index refraction, turns out there exists an angle at which the refracted ray will be exactly at 90 degrees. So let's talk about that. So in this case, let's say here's my boundary. So in this case, here is my normal line. This is my incoming ray. Let's call this guy theta 1. Again, here I'm going from a high index refraction. So N1 here is going to be greater than N2. So again, this thing is going to bend away from the normal line. It turns out that I can tune this thing so that if I come in at exactly an angle, which is what's called the critical angle, what will happen then is that this refracted line will end up going directly along the direction of the boundary. So basically what will happen is if I choose this correct angle here, which we're going to call the critical angle, what will happen then is that a refracted line is going to be directly along the boundary of the surface. So this is going to be my angle theta 2, but theta 2 in this case will be equal to exactly 90 degrees. So in this case, we then have that N1 divided by N2 then must be equal then to what? Sine of 90 degrees divided then by sine of theta critical. Again, this is N1, this is N2. Okay with this? Now, sine of 90 is how much? 1. One of those things. Good. So this is the same thing then as 1 over sine of theta critical, which means from here I can solve for theta critical. So theta critical then is going to be equal to the arc sine of then N2 divided by N1. So this is my critical angle. What's called a critical angle. All right, go. So this critical angle then defines the point at which what? If I had an angle which is then greater than theta critical, what happens in this case is I get what's known as total internal reflection. So if my angle is greater than the critical angle, what will happen then is all the light which is going to strike the surface, none of it then will be refracted on the exterior, which means the only possible choice is it's going to be reflected onto the interior. If my angle is then less than theta critical, some of the light then is going to be refracted through. So let's write that down. So this thing then says that if theta is greater than theta critical, in this case we get total internal reflection. Which means by the time the light then hits the boundary, this thing has an angle greater than theta critical, all the light then will only be reflected on the interior. At which case, this thing will then be reflected at the angle of theta due to our law of reflections. No light will ever be found on the opposite side. In this case, we have no refraction. However, if theta is less than theta critical, we get refraction, as in the usual case. So this is what we call total internal reflection. So basically, total internal reflection will occur as long as your angle theta is greater than the angle theta critical, where theta critical is of course determined solely by the index refractions. So if I know the index refraction of both mediums, I can then determine exactly what this critical angle is supposed to be. And then from there, I can then tune the direction at which I want this thing to hit, and then make sure I either get total internal reflection or I get refraction. Depends on what it is that I want. Now, when do I ever want total internal reflection? Well, I want that if I'm dealing with something like fiber optics. So the way a fiber optic cable works is you actually send the light coming in at an angle greater than the critical angle. So that way you get zero refraction to the exterior. In this case, the only possible choice is that you have total internal reflection, which means all the light will simply travel exactly inside of the original medium at which it is that you sent. Now, if I take that medium and I make it a tube, which is what a fiber optic cable is, then I can send down my lights going from one side of the tube all the way to the other side of the tube with zero loss of transmission, which means I won't lose anything to the exterior due to refraction. All of it's only going to be sent directly down this tube in this case of total internal reflection. This is the way that fiber optic cables work. So the beautiful part about fiber optic cables is when I send a transmission using light from one side of the cable to the other side of the cable, I have zero loss of information, because I have zero loss of energy because I have total internal reflection, making sure all of that information is being sent from one side to the other side. Unlike using regular sources, for example, your internet, if you're using cable internet, in that case, you know you're losing energy due to power radiation because it's current moving from one side to the other side. So in that case, you're losing power due to the fact that you're radiating away thermal energy. Well, with fiber optic cables, you have 100% transmission going from one side to the other side due to the sole fact of total internal reflection. Probably the best example of total internal reflection. So, point of all this is just to note that there is this idea of a critical angle. So if I go from a high index refraction to a low index refraction, I have a critical angle, which means that all of the lights will then be along the boundary itself, where some of it is still reflected internally. Otherwise, if we increase the size over that critical angle, we have only total internal reflection. What's up?
So to find the index refraction, whatever, it's just the speed of light over the velocity of it?
Right, or typically we know the index refractions for particular mediums.
Okay.
So for example, we know light or glass is like 1.5, water is 1.33. So you can choose your materials and then choose your angle from those materials based off of the index refraction. Yeah. So we have measured a lot of these different things already. Okay. So good. So let's use all this and let's do an example. There we go. So a swimmer has dropped her goggles at the bottom of a pool, at the shallow end of the pool, which is 1 meter deep. But the goggles don't look like they're 1 meter deep. They look to be something else. We want to know where do the goggles appear to be? So at what depth are the goggles themselves? So let's do an example. Here's our example. So here is my shallow end of the pool. Good. My goggles are sitting down here. I'm going to draw an infinity sign because that's close enough to the goggle. Great. And I know that this is simply equal to 1 meter deep. Okay? Now my swimmer is going to be looking for her goggles. So here's my swimmer. We have a very, very skinny swimmer. That's my swimmer. Great. And she's going to be looking down to see where her goggles are, but she's going to notice that her goggles aren't at a depth of 1 meter, but they're actually at a depth less than 1 meter, thanks to our fact that we have index refraction, so light is going to be bent differently. So, okay, so what we want to know then is, if this is actually at a height of h, we want to know what is the apparent height, let's call that h prime. So h prime then is equal to the apparent depth. So good. So let's talk about this. So what's going to happen then? So we know what's going to happen is what? To see her goggles, light has to basically come from the sun, go through the water, reflect off the goggles, come back to the surface of the sun, of the water, and then get reflected outward towards her because it's going from a high index refraction to a low index refraction. So basically what's going to happen here is my N1 then is going to be here, which is going to be equal to N of water. Call it NH2O. And then it's going to end up at N2, where N2 is equal to N of air. Now, as we know from lab, N of air is approximately equal to 1, so we're going to choose this then as N equals 1. So, good. So what's going to happen then is what? This light is going to start off here. It's going to come upward, reach the surface, which means it's going to come at some angle. Let's call this guy angle theta 1, not theta 2, not theta 1. But since it's going from a high index refraction to a low index refraction, this guy then is going to be bent away from the normal, and then it's going to come from there into her eye. It's going to be bent at an angle of theta 2. Now, as we discussed, and then draw a line here. What color? So if I draw a straight line here, what's going to happen though is she's going to ray trace the line backwards, because this is what her eye does, and then appears to be located at this location here. So if she ray traces this line backwards, the light has seemed to appear or originated from this particular location here. So she's then going to see her goggles are actually sitting at this location here. So this is where she thinks the goggles were actually sitting. So that this distance here is what we're going to call h prime. So h prime in this case then is going to be the depth at which she thinks they are below the surface of the water. So again, her eye always ray traces things backwards in a straight line. So good. So we want to then determine, okay, so what is h prime here? So let's do that. So to do that, first thing we're going to do is what? Apply Snell's law. So what does Snell's law say? So Snell's law says that N1, which is N water in this case, so NH2O, times sine of theta 1 must then be equal to N air, but N air is simply 1, times then sine of theta 2. So we're going to use this guy from Snell's law. Cool. Now what else? From here, we can also set up some triangles. So here we know this height here is simply h. We know this distance here, and then we can write this as some distance of x. Okay, so let's set up this triangle here. So for this triangle here, what I know then is this distance is x, this distance is h, and that this angle here is simply theta 1, just like the outcoming angle. Simultaneously, we can set up this triangle here. So let me write down this triangle, where this triangle has this horizontal side, which I'm going to call h prime. Still has the same x, but now has this angle here. Well, this angle here is going to be the same as this angle here. So this angle here is going to be simply theta 2. So basically, what I can do then is I can use the fact of these angles to then determine exactly what that height is. Okay, now, in this case, what we want to do then is rewrite sine of theta 1 and sine of theta 2 in terms of these triangles. Okay with us? Now, the way I can do that is I can say, well, sine of theta 1 in this case would be the opposite side divided by the hypotenuse. And then for this one, I can say sine of theta 2 then is going to be the opposite side divided by its hypotenuse. Now, from here, I can make this a little bit simpler by saying that, what? Let's take that distance x is small. Meaning that when she's looking down to see where her goggles are, the distance that she's looking down isn't very far away from her, which means that as long as that angle is small, or as long as this distance is small, these angles are going to be small as well. Are we okay with this? Now, if these angles here are small, as we talked about, in that case, then tangent of the angle is approximately the same thing as sine of the angle. As long as these angles are small, then that is going to be true. So from here, if x is small, then what this means then is theta 1 and theta 2 are also small. So from here, what this means then is I can rewrite this as NH2O times tangent of theta 1 is then equal to tangent of theta 2. So again, as long as these angles are small, sine and tangent are the same thing. Now, how does that help us? Well, that helps us now because now if I'm looking for a tangent of this angle, tangent of the angle is then defined as the opposite side divided by the adjacent side, which I know both x, well, I don't really know x, but I define x and I know h. And then for this one, it's going to be the opposite side, which is going to be x, then divided by h prime, which h prime is what I'm actually looking for. So the only thing it really does for me is it changes the geometry. So now I don't need to know the hypotenuse anymore. I simply need to know the adjacent and the opposite sides. Okay with this? So let's do that. So from here, we can then say that what? This is going to be NH2O times then tangent of h1. So this is going to be tangent of theta 1, which is going to be x divided by h, is then equal to tangent of theta 2, which is going to be x divided by h prime. Okay. Now the x's are the same, so we can go ahead and cancel those x's. Let's do that. And then from here, all we need to do then is what? Solve for h prime, and we can do that by simply inverting both sides. So finally, this tells me that my parent's height then is equal to the actual height divided by NH2O. So the actual height, the parent's height is divided by the actual height divided by index refraction of water. Now, it turns out that the index refraction of water is equal to 1.33, which is equal to 4 divided by 3. So it's 4/3. Good. So from here, we plug that in. So it's going to be then 1 meter divided by 4/3, which is the same thing then as 3/4 of a meter, which means that the apparent depth that she sees these at is about 0.75. So this is the apparent depth of the okay. So good. So Snell's law. So again, Snell's law simply says that if I want to know the angle at which this thing is bent at, all we need to know then is the index of refractions as well as the incidence angle, and then from there we can define or determine the whole. So last thing we're going to look at for today is another interesting topical effect that we can get, which is what's known as thin films. So this is what's called thin film interference. So basically, anytime you're in a parking lot and you see somebody's car has dripped oil and then that oil mixes them with water, and you look at it from different angles, you can see all kinds of pretty lights, almost like a rainbow inside of the oil, inside of the water. Or if you look at the bottom of a CD, you can see all kinds of different colors, depending on the direction at which it is that you're looking at the CD. So this is what we call thin film interference. So basically what happens is these things are creating what's known as a thin film. So it's a very, very thin layer of some sort of material which has an index of refraction. Now, ultimately what's happening here is what? This is an air out here. Then I have a very thin film which has an index of refraction. And then underneath of that, I have another material which has another different index of refraction. So for example, this is oil sitting on top of water. Then it has air on the outside. Oil has its own different index of refraction than from water. Now, what happens in this case then is that the light is coming in, striking then this top surface, which means that I'm getting some reflected light coming back from the top surface. Some of that light then will be refracted through into the second medium, which in this case will be the oil. It's going to go through and then hit the bottom of that, which now hits another boundary, which then is going to give me another reflected light coming off of there. And then that reflected light is then coming out, interfering with that originally reflected light, which is then causing me to see different color patterns. Now, the way this works is dependent on what type of boundary that I have. So just to remind you of the different types of boundaries we can have, let's go back to this beautiful thing here. Something we looked at a long time ago. So remember when I talk about different boundaries, I have different types of things that happen with different boundaries depending on if I have a fixed boundary or an unfixed boundary. Now, if I have a fixed boundary, let me run this thing. Just remind you what happens when we have a fixed boundary. If I have a fixed boundary, what happens in this case then is that what? The reflected wave is completely out of phase with the original wave. So in this case, it's a 180 degrees phase shift, which means that my reflected wave is out of phase from the original by 180 degrees. However, if I have an unfixed boundary, what happens in this case then is what? My reflected wave comes back in exactly the same phase as my reflected wave, or as my original incoming wave. So why does this matter? Well, this matters because light is going to be hitting different boundaries, which means it's going to be hitting different index of refraction. Now, what that means is if I go from one index of refraction to another index of refraction, that index of refraction is going to act as one of these two boundaries. Meaning, if I go from a low index of refraction to a high index of refraction, that acts as if it is a fixed endpoint, which is what we originally saw. Which means in this case, the light that is reflected off will be 180 degrees out of phase from the original light. However, if I go from a high index refraction to a low index refraction, that low index refraction acts like an unfixed boundary, which means the light which is reflected comes back in the same phase as the original light. So, a lot to take in at one point. But what we see here is going to be dependent on these index of refractions because it's going to be dependent on is the light reflected out of phase or in phase with the original light, depending on the sizes of the index of refractions. Okay. There's a lot of things to kind of think about while we're looking at these things. So let's talk about our thin film. Let's take a thin film interference. So what happens with thin film interference? Well, again, I'm going to have two different boundaries because I have three different materials. So here I'm going to have index refraction N1 on the outside. My second medium is going to be index refraction N2, and then my final is going to be then N3. Now, in our cases, we're going to look at the fact that light is going to originate in the first medium of N1. So my incident ray is going to come in and strike this medium here. Means I'm going to establish a normal line here. Now, what's going to happen? Well, this light here is then going to be reflected. So part of it's going to be reflected, and let's call that ray 1. So ray 1 is going to be reflected, and we know by the law of reflections that this angle here is exactly the same as this angle here. But part of that is going to be transmitted. That part that's going to be transmitted then is going to come down here, strike this surface here. Part of it's going to be then reflected back off in this direction. And then it's going to be transmitted through this boundary and then come back in this direction. And let's call that guy ray 2. Now, again, we know what's going to happen here is that this is going to have a different angle here. So let's call this angle phi. And then this angle here is, of course, going to be the same angle of phi. Because law of reflection says this angle has to be the same as this angle. But again, depending on how this is going to move, it's either going to be more towards the horizontal or more towards the normal or away from the normal, depending on the size of those two guys. Now, ultimately what ends up happening then, again, is I am going to get some transmission down through here. Let's call that, what color I'm going to use yet? Let's use that yellow. This is going to go down into medium number 3, but ultimately we don't care about that. Now, what's going to happen then is my eye is going to be sitting somewhere out here. This is my eye looking at what actually happens. Now, what's going to happen then is I'm going to get interference then between ray 1 and ray 2. So this is what we call the thin film interference. Now, certain colors are then going to be destructively interfering, while other colors are going to be constructively interfering. So that's again what gives me this picture here. What I'm seeing then are the ones which are constructively interfering. So in that case, I'm getting maximum amount of amplitude. So I'm seeing the maximum amount of frequency from that one, which is why I see this location here looking orange. Or other ones are going to interfere destructively, which means I'm not going to see them. Now, the way that this happens is going to depend on two things. Number one, the path length difference. So what's going to happen here is since these two rays are coming out parallel to each other, then the path length difference in this case is simply going to be twice this amount of distance here. Now, for us, we're going to pretend that this angle here is so small that the distance at which this thing travels, we're not going to care about the horizontal distance. It's only going to be the vertical distance in this case. So we're going to say that this thing hits almost perpendicular to the surface. So in that case, this thing only travels straight up and down. Okay. So in this case, let's say this has a thickness of L to it. So in this case, we're going to say that our path length difference of delta L is simply going to be equal to twice of the length. So we're going to pretend that it's coming in with such a small angle that it's approximately at a 90-degree angle, or in this case, 0 degrees. Now, from here, the type of interference that I get out here is going to be dependent now on the ratio then of these indexes of refraction. Now, what's going to happen? Now, again, if I go from a high index refraction to a low index refraction, we're again going to get no phase change. In that case, this thing acts as an unfixed boundary. So we go from a high index refraction to a low index refraction, the wave is going to be in phase with the original. So in this case, if we go from a high index refraction to a low index refraction, there is no phase change. However, if we go from a low index refraction to a high index refraction, in that case, there is a phase change.
How'd you get 2L back?
Oh, so again, in this case, what I'm saying is as long as this angle is close to 90 degrees, what happens then is that this light ray is only coming down, hitting L, and then coming back distance of L, and then refracting outward. So that's my path length difference. So it's just this distance twice. So that's why it's 2L. Okay. So what's the point of all that? So the point of all that is what? Let's say I get a phase change here, but I don't get a phase change here, then constructive interference occurs when what? I have half an integer difference between the wavelengths, as opposed to destructive interference, which is going to occur when I have an integer multiple between the wavelengths. But if I get a phase change here and a phase change here, in that case, then I get double phase changes, which means that the index of refractions are different, which then causes what? My constructive interference to then become the wavelength times an integer multiple. And then destructive is going to be half integer times the wavelength. Or if I have no phase change and no phase change, it goes back to the original one. Okay? So here I have to pay attention to not only the path length difference, but how the index of refractions line up with each other, because that's going to determine the total number of phase changes that I have. And then a total number of phase changes is going to depend or determine what type of interference I get. Whether I get constructive interference versus destructive interference. Okay? So let's write all that down. What does that mean? So this means that if I have no phase changes or two phase changes, in this case, my path length difference, delta L, which is then equal to twice the length, would then be equal to what? Integer multiple of the wavelengths, or then a half integer multiple of the wavelength, all then times for constructive interference and then for destructive interference. However, if we have one phase change, in this case, my path length difference, which again is going to be equal to twice the length, is then going to be equal to then n plus a half times the wavelength, or n times the wavelength, or constructive versus destructive. So the point is that these two things are going to switch depending on the total number of phase changes I have. So again, if I have no phase changes or two phase changes, in this case, my constructive interference stays the same from what we saw before. So does my destructive interference. But if I only have one phase change, then my destructive interference becomes my constructive interference, and my constructive interference becomes my destructive interference. Now, one other thing to point out here. Notice that this wavelength here isn't the original incoming wavelength, but it's the wavelength of the light while it's in the second medium. So why is that? So initially, this light is coming in with some initial wavelength. Well, what happens? Now, remember when we talked about waves a long time ago, what we know is that the frequency in each medium stays exactly the same, which means the frequency here is the same as the frequency here, which is the same as the frequency here. But since this index refraction is different than this index refraction, which is different than this index refraction, means the speed is different here than it is here, which means it is here. Which means that, remember that the velocity is equal to the wavelength times the frequency, which means that the velocity is different, but the frequency is the same. That means the wavelength has to be different. So what that means then is that this wavelength here is different from the initial incoming wavelength by simply the index of refraction. So the index of refraction changes then the wavelength, which means the wavelength inside of the second medium becomes the original incoming wavelength divided by the index of refraction of that second medium. Okay with this? So then guys, so here again, we have to pay attention to multiple things. We have to pay attention to the path length difference, which is simply going to be twice the thickness. But then we also have to look at how do the index refractions all line up with each other. How many phase changes do I have? Do I have one phase change? Do I have two phase changes? Do I have no phase changes? And again, the way I know the number of phase changes is, again, if I go from a high index refraction to a low index refraction, that is no phase change. But if I go from a low index refraction to a high index refraction, that is a phase change. So let's do an example. Let's kind of see how all this works. So this says I have a thin film of acetone, which is 1.25 index refraction, coats a thick piece of glass, which has its own index refraction of 1.5. White light is incident to the film. So if the reflections, so in the reflections, fully destructive interference occurs at 600 nanometers and fully constructive interference occurs at 700 nanometers. From this, we want to determine what is the thickness of the acetone. So okay, let's draw our picture. So here is our system. So we have N1 then is simply equal to N of air, which is going to be equal to 1. Then we have N2, which is equal to N acetone, or the Na, which was equal to 1.25. And then below that, we had what, glass. So we had N3 was equal to N glass, which was equal to 1.5. Now, what is this telling me? So this tells me that what? Destructive interference occurs when I have a wavelength, an initial wavelength, λ1, which was equal to 600 nanometers. And then constructive interference then occurs when I have λ1 was equal to 700 nanometers. So in this case, what it wants me to determine then is what is the thickness of the acetone, which is what earlier we called the length. So in this case, I'm just going to say the length of this is equal to the thickness. Okay? So good. So let's apply what we just learned. So first things first is we're going to look at how many phase shifts do I have in this case. So in this case, I'm going from a low index refraction to a low index refraction, or to a high index refraction. So I'm going from 1 to 1.25, which means is the original ray, the original reflected ray, is that guy phase shifted or not? So we go from low index refraction to a high index refraction. Is that guy phase shifted or not? Yes. So here, my ray 1 is phase shifted. So now I have one phase shift. Now the second ray, which is going to come from here, also is going to go from a low index refraction to a high index refraction. And do I get a phase shift going from a low index refraction to a high index refraction? Yes. So I have actually two phase shifts in this case. So ray number 1 is going to be phase shifted by 180 degrees. Ray number 2 is also going to be phase shifted by 180 degrees, but those two phase shifts are going to cancel each other, which means that in this case, constructive interference will stay usual constructive interference, and then destructive interference will stay usual destructive interference. So what does all this mean? This means that for us, the path length difference then is going to be equal then to n times lambda 2 for constructive interference, and then n times plus a half times lambda 2 for destructive interference. Okay. Now, let's use the information that we know. So in this case, what we know is that what? We know when this thing had destructive interference, this corresponded to a wavelength of 600 nanometers. So good. So let's write that down. So in this case, we know our path length difference, which is going to be twice the thickness of the acetone, then is going to be equal then to, for destructive interference, n plus a half times then lambda 1 divided by n2. Okay with us? Now from here, we know n2, we know lambda 1, but we don't know n. If we knew n, we could easily find the thickness of the acetone. But in this case, we don't know what n is. So let's look at the constructive interference. So let's look at our constructive. So for us, we know that delta L, which is going to be equal to twice the thickness, then is going to be equal to n times then lambda 2, which is the same thing then as n times lambda 1 divided by n2. So here, we know lambda 1 now is simply equal to 700 nanometers. We know n2 is still 1.25. But we don't know what n is again. Okay? Now, from here, the best thing to do then is what? Start choosing different values of n, and then simply calculate a few values of the thickness based off of those different values of n. Here, we do the same thing. Choose different n values, and then from here, calculate different thicknesses. And then eventually compare those two thicknesses to each other, and then find two that are the same. Once we have two that are the same, we know that has to be the thickness of our acetone. That make sense? So all we're going to do here is we're going to start off with our destructive interference, and then start off with n is equal to 0, and then do n is equal to 1, and then n is equal to 2, and then etc. So if I do that, what I find is, in this case, when I do it for destructive interference, when again is that what? The thickness then is equal to 120, 360, 600, 840, etc. nanometers. And then for constructive interference, we find in this case then is that for n is equal to 0, n is equal to 1, etc. We get then that the thickness is equal to 0, 280, 560, 840, and etc. nanometers. Then what I'm going to do is start comparing these guys and see, do I have any that are the same? Well, here I get what, 0 and 120, that's not the same. 280 and 360 is not the same. 560 and 600, that's not the same. But 840 and 840 are the same. So this means then is that my thickness of my acetone must be equal to 840. So this is my thickness of the acetone. All right. Okay, so what's today? Wednesday? Yes. Okay. Tomorrow we'll start off with another example of this, and then I'll have some group assignments for you guys to work out in there for some examples of these things. And then we'll start moving on. How you doing, Tim? Good. Fun.